combinations and permutations. Okay, yeah, we're going to open up our notes, and after, we just want to look at a couple problems here in page 35. So I briefly mentioned while you're writing your quiz that there's three concepts we've learned so far, right? We've learned about fundamental counting principle, which we always have to use that case when we have repeats. When we don't have repeats, we could still use fundamental counting principle sometimes, but we want to really ask ourselves, does order matter or not? Okay, is this a permutation or a combination? A permutation is when order matters. That's when we make sequences or arrange letters in a word, or I'm placing you in specific positions. So somebody's going to be president, somebody's going to be vice president, and someone's going to be the class clown. Okay, right? If I put you in actual specific spots. Okay, thank you. So that is a permutation. A combination is when I just want three of you. Okay, you're not going in specific positions. We're not placing you in a certain order, but I just want three people, and I choose three people. So how I arrange you doesn't matter. Just who I have matter. Or if I have, like, I'm playing a card, a deck. Often I use cards is used because that's usually something that people understand in our culture is playing cards, right? When you hold a hand of cards in your hand, like in your hands, a hand of cards in your hands. Yeah, sounds funny. It doesn't matter the order, right? You may arrange it any ways. You have those 5 cards. It doesn't matter how they sit in your hand. What matters is who's in your hand. So let's talk about, I want to look at number 1 and then maybe number 3. Okay, so on page 38, how many definitions are there of 3 objects chosen from a set of 5? So how did we solve this problem? There's 2 ways we could have solved it. We could use fundamental counting principle, and so how many spaces would we have? 5 or 3? We'd have 3. How many options do we have for the first space? 5. Okay. How many options do we have for the second space? 4 and 3. Okay, so 5 times 4 is 20. 20 times 3 is 60. We could have also solved this another way. We have 5 objects and we want to pick 3. It's a permutation. So order matters. And in our calculator, 5 pick 3 is also 60 arrangements. Okay, now I'm not going to write out all 60. So how many different ways are there of arranging each subset of these 3 objects? So what I mean by that is we know there's 60 arrangements of picking 3 out of 5. Okay? Now those 3 that we've chosen, how many ways can I arrange those 3? So say if my 5 objects are A, B, C, D, and E. Okay? Let's say we have A, B, and C. How many ways is one of the subsets? How many ways can we arrange A, B, C? How would you figure that out? 3 what? 3 factorial. Remember, to arrange n objects, we have n factorial ways of doing that. It'd be 3 factorial, right? There's could be A, B, C. We could have A, C, B. We could have, B, A, C, B, C, A, and then C, A, B, C, B, A. There's a total of 6. 3 times 2 times 1. 6 ways of arranging that subset of the 3 that I've chosen. Are you with me? Okay, so I want you to, in the number 1, there's 60 ways we can actually, a total number of arrangements we can make. When we have a subset, when I choose 3 of you, how many ways can I arrange those 3? There's 6 ways. So in a combination, are these any different from each other? Or are they all the same thing? If order doesn't matter. If order doesn't matter, so in a combination, these are all the same thing. in a permutation, they're different. Order matters, right? ABC is not the same as ACB. But in a combination, those are all the same things. So how do we get how many total combinations are there? How many different combinations are there of 3 objects from a set of 5 different objects? Well, if we know there were 60 different permutations, okay, there's 60 different permutations, and each subset has 6 that are identical. We're going to divide that by 6, or 3 factorial, okay, which is 60 divided by 6 gives you 10 combinations. So what's really important here is to note that when we are dealing with a combination, these are all the same. So I need to eliminate those repeats, okay? Because these subsets, ABC is the same thing as CAB. It doesn't matter the order, just who's in our group, okay? And so if we came up with all the different combinations would be an example if I was using A, B, C, D, E. One combination would be A, B, C. Another combination would be A, B, D, A, B, E. There's going to be 10 of them, right? Notice that there's no repeats in, like, the letters, the order doesn't matter, just who's in the group. There's going to be 10 of those. I could do, is that all the A's? A, then C, D, A, C, E, and then A, D, E, and B, C. We can go through the list. Those are the combinations. There's still 5 more. B, C, E. What am I missing? To look at who's there. A, B, C, D, E. B, C, D. I mean, keep going. There's going to be 10 of them, right? Doesn't matter the order of ABC, just who's in it. That's a combination. Turn the next page. Okay. So number 3, I want you to write out all the permutations of 3 letters from A, B, C, D. Okay, all the different permutations. So here's a hint when you're doing that. I would start with A, B, and C. And then I go A, B, D. Let's do all the ones with A, B, C actually, because we're doing permutation. Does order matters with A? Permutations, order matters, okay? So yes, order matters. So A, B, C, is that the same thing as A, C, B? No, those are different. So let's do those ones first. So A, B, C, A, C, B. We can also do A, B, and D. A, D, B. What's another one? A, so we have A, B, C. We had A, let's keep all the ones with A right now. So we have A, B, C. We did the one with A, B, and D. How about A, C, and D? And then A, D, C. So those are all the ones, all the permutations with A as the first letter. Now let's do all the permutations with B as the first letter. So B, and then choose 2 letters. AC, and then B, C, A. Now we'll do B, B, C. You want to do B and C, D? Sure. Sorry, I didn't hear. And B, D, C. What's the other one with B as the first letter? B, and what other 2? A, D, and then D, A. Okay. And now we'll do C as the first letter. So there's going to be, notice there's always 6 of them with C as the first letter. So now I'll go C and A, B, B, A, C and A and D, D, A, and then last would be C and B, D, D, B. And then last, D is the first letter, there'll be 6. Okay. So D and A, B, B, A, D and A, C, C, A, and then D and B and C. B, C, C, B. So how many total different permutations is that? 24, because there's 6 here, 6, 6, 6, and 6 times. So 6 times 4 is 24 permutations, or 24 arrangements. Now, if it was a combination, so if it's a combination, would these here in this first group, would they be any different from each other? Or would they be the same thing if it's a combination? Just who's in the group, doesn't matter the order. Those would all be the same thing, right? ABC is the same thing as ACB. If I just want those 3 characters, doesn't matter the order, these would all be the same thing in this first group. These in the second group would all be the same thing. These would all be the same, and then these would all be the same. Oh, no, I circled that wrong. No wonder you guys are like looking at me crazy. I'll find all the A's and B's and C's. So these would be the same, right? There we go. Yes. You're like, what are you talking about, Miss Johnson? Yeah, these would be the same. All the ones with A, B, and C. So where's all the ones with A, B, and C? Is there any other ones with A, B, and C? Or are those the only ones? I'm going to use a smaller highlighter. So ABC, ACB, BCA, BAC, CAB, CBA, and that's it. So these here would all be the same, right? Would you agree with that if the order didn't matter? Okay, so that group of 6 right there would all be the same thing. There's another group. Okay, what about the ones with A, B, and D? 1, 2, how many of those would we have? ABD, ADB, where are BDA and BAD, and over here, right? DAB and DBA. Those would all be the same thing as well. So write out all the combinations of 3 letters. So what are all the combinations of our 3 letters? So one of them we said was A, B, and C. What's another combination of 3 letters? A, B, and D. Okay, what else? Another combination of 3 letters. Doesn't matter the order. A, C, D, and B, C, and D. So there's 4. There's 4 different combinations. Okay, notice the difference between a permutation where order matters and a combination where order doesn't. And so a combination, we could figure it out by figuring out, okay, how many total permutations divided by those arrangements that are repeats. And those arrangement are repeats here with 3 letters, there was 3 factorial, 6 ways that were repeats. Okay, so notice that the permutations was 6 times more than the number of combinations. Or, what factorial is equal to 6? 3 factorial. 3 factorial are 6 times more permutations. Because once you group those 3 letters together, there's 3 factorial ways of arranging them if we wanted the arrangements versus a combination. Open up your notes now to 2.6. I wanted to just kind of lead us into what is a combination versus what's a permutation. 1 second. Oh, this was from the last day. What I want you to write is this instead. Consider a 5-card hand. Two 5-card hands, actually. All right. So hand 1. Give me a card. Give me a card. Tell me a card in the deck. A what? A joke. Okay, other than a joker. Of course you throw that one in there. So 52 card deck, excluding jokers. We always exclude jokers unless they state. Give me a card and a suit. Ace. Okay, we have 2 clubs, and so 2 of clubs and an ace of spades. Okay. Okay, I need another card. Tell me a card. King of diamonds. Okay. Throw in another one. 6 of diamonds. Let's get a heart in there after. 4 of hearts. Let's do this. And you can do 6 too. 4 of hearts. Okay. So here's hand 1. Hand 2. I want you to write king of diamonds. And then we have ace of spades. Oops. Spades are hard to. Upside down hearts are not natural. Ace of spades. So we have king of diamonds, ace of spades, 6 of diamonds, 2 of clubs, and the 4 of hearts. Okay. Are these any different? Is there a difference between the two? Yeah. Okay, so it depends. It depends if we're asking if order matters or if order doesn't. So in the case of cards, will order matter? Order will not matter. Unless I ask you to arrange the cards, right? Unless we say, let's arrange these 5 cards, then order matters. But in the case of just holding a hand, in the case of the cards, order will not matter. And therefore, there is no difference in this if we're not arranging them. They are the same. Okay, they are the same. So combinations, there's 2 ways to write this. So remember how permutations we have the letter P? Conveniently, for combinations, we have the letter C. You can solve counting problems where order is not important by calculating the number of combinations. The number of combination of n different objects where r of them are used in a combination. So often we use the word chosen versus permutation. We often use the word pick. You notice P and C. Okay. So there's 2 ways to write this. NCR, or these are both the same thing. This is still n choose r. Okay. And the number of combinations of n objects where we want to choose r of them. Okay, you need to know both notations. They can both show up on your diploma. So both are expected of you. Okay, so note it. Let's just really quickly. I don't know if you remember the formula for NPR. It was n factorial over n minus r factorial. That was the formula for the number of permutations. So if it was 5 pick 3, 5 times 4 times 3, it's because it was 5 factorial over 2 factorial, right? We had 5 pick 3, 5 times 4 times 3. We could also write that as 5 factorial over 2 factorial, or 5 factorial over 5 minus 3, which is 2 factorial. That was the formula for permutations. What's the one difference between our permutation formula, when order matters, and our combination formula? Order does not matter. You see the one difference? Where's the one difference? There's there's an r factorial in the denominator. So notice that there's r factorial, okay? We're dividing by an additional r factorial. And this is what we were talking about in those questions we were just looking at. We need to, if we are picking, or choosing, sorry, 3 objects, their arrangements don't matter. So we need to divide by, if there's 3 objects, 3 factorial arrangements don't matter. So subsets, we often call them, are repeats since the order does not matter. All right, so this part right here, subsets are repeats since order does not matter. And so really it's the number of permutations divided by the number of subsets that are repeats. So if we're picking or choosing 3 of them, there's 3 factorial repeats because their arrangements won't matter. And so this is the formula for choose. So for example, if you have 3 choose 2, it would be 3 factorial over 3 minus 2 factorial. That's the perm part. And then also divided by 2 factorial. These are the subset repeats. Okay, that's the formula. Now, could you use your calculator also to solve these? Yes. Just if I wanted to type this in your calculator, everyone grab your calculators. You would first push 3. Guess where you're going? Conveniently. Math, just like before. Oops. Let's open this one. Math. 3. So math, then we have to push. So how many objects? So 3, math, then left arrow to probability. And number what? 3? Number 3 is we want to choose NCR for combinations. And then 2 is how many objects we're choosing, and enter. So in our calculators, number 3, and so 3 choose 2 is equal to 3, okay? Or 3, right? So that's our calculator stuff. So note, so combinations and permutations assumes no repeats, okay? Always with a combination, just like a permutation, no repeats allowed to use a combination type problem. Because if you're choosing people, you can't have a clone of them, right? Or if you're choosing a car, there's only one of them. So assume what do we use? There's a problem with fundamental counting principle. Yeah, we use just put in our dashes, right? Like usually like the digit problem, digit, letter. 26, 26, 10 of them, right? We just use the fundamental counting principle. Okay, turn the page. So in all of this, instead of going through all of this, we're gonna go through some problems, but I will highlight that the formula for NCR is the formula of NPR divided by R factorial. Why? Because dividing by R factorial eliminates the counting of the same combination of R objects arranged in combination of R objects arranged in different orders. Eliminate those subsets where ABC is the same thing as ACB. I had to think that one through. Okay? All right, let's go to some examples. Joe has a choice of 4 flavors. We have vanilla, strawberry, chocolate, and butterscotch. Okay, those are the 4 flavors. List all permutations for a 2-flavor sundae. So in a permutation, does the order that they put the ice cream together matter? Yes, the way they scoop it matters. You are very, very particular because maybe you want to have like strawberry first and then have the strawberry like bleed into the chocolate a little bit, right? Maybe you want to save the best for last. Go on my desk, please. right? So who knows? Okay, so can you please list all different permutations, all arrangements of choosing 2 of these from the 4? So I'll give you the first 2. I could have vanilla, then strawberry, or strawberry, then vanilla. So list them all. So start with all the ones with vanilla first. So I don't know why you choose vanilla when you got chocolate and strawberry there. It's not. We're just going to talk more about the difference. Yeah. It's easier to calculate it, for sure. Yeah, it makes a difference. Or maybe if it's in like a cone, you want your like vanilla cone to mix with chocolate. I don't know. These things matter. Sometimes. For some people. Okay. Vanilla chocolate, chocolate vanilla. No. So we're assuming no repeats. Yes, that's a very good question. That'd be a whole nother question. Vanilla butterscotch, butterscotch vanilla. And then do now all the ones with, so we already did all of these. So now strawberry chocolate, chocolate strawberry, strawberry butterscotch, butterscotch strawberry, and then chocolate butterscotch, butterscotch chocolate. I think that's all of them. Yes? How can we check our answer? Well, there's 4 different flavors, and how many are we picking? 2. So by the formula, that's 4 factorial over 4 minus 2 factorial, or 4 factorial over 2 factorial, which is 4 times 3, or 12. Okay, 12 arrangements. All the combinations, well, we don't really have to go through much work, because are those the same thing if it's a combination? If it doesn't matter to you the order, just the flavors that you're picking, yeah, those are the same. These would be the same. Those would be the same. So how many different combinations would we have? 6. We'd have 6, right? Vanilla strawberry, vanilla chocolate, vanilla butterscotch, strawberry chocolate, strawberry butterscotch, and chocolate butterscotch. Those would be our 6 different ones. So in your calculators, let's just double check. 4 choose 2. So 4 choose 2 is 4 factorial over 4 minus 2, which is 2 factorial, and then divided by the arrangements that are repeat. There's 2 factorial, right? Each one of these subsets, there was 2 ways to arrange those, and that's why we have to eliminate that, which gives you really 6. 4 factorial over 2 factorial was 12, divided by 2 is 6, or in your calculator is 6 as well. Okay, so there's 6 combinations. So number of 2 flavor permutations, so how are these related? The 6 combinations and the 12. How many times greater? There are 6 combinations and 12 permutations. So 12 was how many times greater? It's 2 factorial, right? Or 2 times greater. Because there was 2 factorial ways of arranging the subsets. Because we had 2 letters for choosing 2. Since there's 2 factorial ways of arranging each group, there was 2 factorial ways of arranging each group of 2 chosen. All right. Next page. Let's go through some problems. So on the next page, can you just type those into your calculator, solve the next 2? Or you can use the formula if you like. So if you want to use the formula, n factorial over n minus r factorial times r factorial. Can we wait? Okay, or use your calculator. So 5 minus 3 is 2 factorial over 3, our r is 3 factorial. Or with your calculator, 5 math, 3, and we want to choose 3 of them. Okay, 10. So what does this mean? How many objects? 6, and we want to choose? How many combinations can we make with 4 of them? Out of the 6. So 6, math, left arrow, 3, and 4. 15. Okay. 15 combinations. Again, if you wanted to use the formula, it'd be 6 factorial over 6 minus 4 is 2 factorial, and then divided by the 4 factorial. And that would also give you 15. So this on B, because that symbol is always a combination symbol. Okay, so that's just another way to write for combinations. You would never see that as like permutations would always be a P. It would always be written this way here, but with a P. Okay. A restaurant serves 10 flavors of ice cream. Lots of ice cream today. Danielle has ordered a large sundae with 3 scoops of ice cream. How many different, so that's a key word here, and that's what should have been in that other problem, Kamisha, that you pointed out, right? How many different ice cream combinations? So different meaning, what does that imply? No what? Repeats. Okay, so now that we know it's no repeats, it's either going to be a combination or a permutation. So the question is, does order matter here? How many different ice cream combinations does Danielle have to choose from if she wants each scoop to be in a different flavor? So here, the key word is combinations. Okay, so they tell us it's a combination. So that means what? Order does not matter. If it's a permutation, you'll hear words like how many arrangements or how many sequences. Yeah? What? I have no clue where that came from. Maybe I need a drink. Maybe subconsciously I need some water. Yeah, probably. Okay, so very simply, 10 flavors. We want to choose how many? 3. Okay, pretty simple. 10, math, left arrow 3, and 3. 120. Yes. Combinations. Now, interestingly enough, I want you to type in, let's just see this. 10 choose 7. What do you notice? Do you notice it's 120 as well? Okay. So what's interesting about combinations, if there's 120 ways of choosing 3, making combinations of 3, there's also 120 ways of not choosing 7 or choosing 7. Okay. The thing about combinations, when you choose 7, you're eliminating the 3 every time. Okay, so they're going to be the same, right? So, for example, if I had 5, let's go 6, math, choose 2, that will be the same way. How many ways can I choose 2? I'm also then not choosing how many? 4. 6, math, choose 4. Okay, so notice the R value, add to 6. So whenever I choose 2 objects from 6, I'm also not choosing 4 objects from 6. So those number combinations are the same. And that's something you're going to see when you're solving algebraically in the future, okay? All right, next page. Last page. It's a long one today, sorry guys. Tanya. Tanya is the pole push team. I don't know. I have no clue. That consists of 9 players. We have 5 male and 4 female. In each competition, reams of 4 compete against each other to push their competitors out of a circle. The team that is successful wins. Okay? So you're going to go up against 4 people. It's kind of like if you're figure skating. Does the order matter in which you compete? No. Just who's in that 4 matters. Okay? So reams of 4 compete. A, how many different 4-person teams does Tanya have to choose from for an all-male competition? So if it's all male, how many males are there? There's 5, and how many do you want to choose? How many combinations we want? We need them in groups of how many? 4. So 5 choose 4. 5 factorial divided by 5 minus 4 factorial, or 1 factorial, 4 factorial, is 5. Or if you type that into your calc, so there's 5 possible 4-person teams. Okay, remember order doesn't matter. If you wanted to check that, you could go name them like A, B, C, D, E, and write all the different combinations of the 4 of them. Okay. Now the next one says how many different 4-person teams. So again, you can't repeat a person. Does Tanya have to choose from with 2 males and 2 females? Okay. In and, what does that imply in multiplication? So we have our 2 females and 2 males. You're only going to use addition when you have or, which is a situation where you have different cases. So if I said, how many 4-person teams can Tanya choose from if there's words like at least 2 males? So at least 2 males, there's different cases, right? You could have 2 males, you could have 3 males, or you could have 4 males. So you'd have to find each one and then add them together, solve them separately. So when you use or, addition, is only when we have separate cases. There's only one case. She wants 2 males, 2 females. So from the females, how many females are there? There's 4 of them, and we want to choose 2. And males, there were 5. And again, we want to choose 2. Okay, yes, you can enter this in your calculator all at once. You don't actually. So for math, left arrow 3, choose 2 times, and I'll show you after, it gives you the same. 5, math, leftover, arrow, choose 2. Okay, and that's 60. So if you solve them separately, 4 choose 2 is equal to 6. 5 choose 2 is equal to 10. 6 times 10 is 60 combinations. Okay? I want to give you one more question. And I know, and then I promise we're done. Because you're going to come across this in your homework and on your test. So example 5, you'll have room just to write it right there. There's 2 parts. Part A, how many 5-card hands are there with 3 black cards and 2 red? Okay, that's A. So we want 3 black and 2 red. Okay, so in a deck of cards, how many black, so there's 52 cards in the deck, right? How many red? Told you know? And how many black? It's half and half. So if there's 52 total, there's 26 black and there's 26 red. There's 4 suits, right? What are the suits? Does anyone remember? Clubs, diamonds, hearts, and spades. Okay, and there's 13 in each suit. These are all suits, and there's 13 in each suit. Okay, so when it says 3 black, we want to choose. How many total black do we have? 26, and we want to choose how many of them? 3 times. There's how many reds? 26, and we want to choose 2. Okay, so type that in your calculators and see how. Yeah, it's going to be large. There's a lot of cards, so there's a lot of combinations. So expect it to be large. 26, choose 3, because we're doing this and that, 3 black and 2 red, so we're multiplying. So we only use addition if there's more than one case. 26, choose. Oops, sorry. Math, probability 3. There you go, choose 2. Did you get 845,000 combinations? You did. That is correct. Okay, so whenever we're dealing with hands, order does not matter, right? So we're using choose because order does not matter whenever we're dealing with choosing a deck 5-card hand. Now, this is the key question I really want to focus on next, okay? How many 5-card hands have at least 3 blacks? Have at least. So if you hear at least or at most, you have different cases. At least 3 black cards. Okay, what are our cases? Case 1. Give me one of the cases. 3 black and 2 red. Okay, case 2. It's at least 3. 4 black, 1 red. And case 4, or case 4. I can count. 1, 2, 4. 1, 2, 3. Third case is 5 black. You could write 0 red. You don't have to. You could just write 5 black. Okay, so if it's at least 3 black cards, you could either have 3 black cards, 4 black cards, or 5 black cards in a 5-card hand. So we need to find each one of these combinations and then add them together, because it's going to be case 1, or it's going to be case 2, or it's going to be case 3. Yes. No, because we're making how many 5-card hands? Yeah. So case 1, 3 black. We actually did that one before. The 3 black, well, there's 26 black. Choose 3 times 26 red. Choose 2. Plus case 2. Case 2, how many blacks total are there? Still 26. Choose 4 times 26 reds. Choose 1. Plus case 3. So you're welcome to solve these independently and then add them together. You could technically type this into your calculator all at once. You might make a mistake though. Okay, and the last is we just want 5 blacks. So there's 26 blacks, choose 5. You're welcome to multiply by 26, choose 0. It's equal to 1, so it doesn't change your answer. Okay, so there's our 3 cases. So let's do one at a time and then add them together. So the first one, we actually just did this one, right? 26, choose 3, 26, choose 2 in the previous question, and that was 845,000. Less. Now, on your calculator, if you want to save time, go second, move it over here. Second, enter. Okay, so I can go back now and change this now to 26, choose 4 times 26, choose 1. That's going to save you some time. 388, 700, 1,700 plus, and then go second, enter, 26, choose 5, and then you can delete this or make this 26, choose 0, because we want 0 red cards, 65,780, so we want to add these all together. So plus 388,700 plus the 845,000. 1,299,480. A lot. They could. Oh no, like this? Yeah, or yeah, exactly. Or if I say to the nearest million, it's 2 million. Sorry, I can't round. It'd be 1. Rough day. Okay, so, or yeah, there's ways to do it. Definitely. You could have typed this in all at once. If you want me to see me do that, it's fine. Your calculator knows BEDMAS. So if you did type this in all at once, you get the same answer. It just, you're more likely to make a mistake because it's a lot of typing. So, and then plus 26. See how fast I can, oh no, I'm not that fast. See, I'm already making mistakes. Choose 4 times 26, math, choose. Anyways, your homework is, you can open up your homework. While I, see, I use P. And choose 5. Okay, so there is a way to type it in all in your calculator once. It's possible. You're just more likely to type something in wrong, but you can if you like. So your homework, omit number 5, so it's 2. You don't have to do any of it. The rest of that is extra practice if you would like. So your homework is on page 41 to 43. Please omit number 5. Okay, omit number 5. Alrighty. So starting to wind down, okay, which is good. So that means tomorrow's lesson is really just a continuation of combination type stuff. And the difference, when do we know the difference? When do we use permutations? When do we use combinations? And then 2.8 is actually just going to be more practice with this stuff. So we're really starting to wind down in this unit. Your test, do you know when it is? Yeah, it's April 25th. It's for you guys.